Well, welcome back, everybody. Hope everyone's doing okay. Everybody being safe and so forth. A couple of things I want to talk about before we continue. First of all, we're going to continue with chapter 6, and we ended up on slide 16 on chapter 6. We'll knock that out today, and then we'll get into 7. But before that, let's take a look at the screen, and we'll look at the what's coming up. Today's the 19th, obviously lab number 4, and we got a couple activities. Now we don't have schedule until, I'm gonna let one more person in, until the weekend of the 6th, where we have exam number 2, which would consist of chapter 4 through 6. So you got plenty of time to prepare for that. So take a look at your schedule. Now, the other aspect is this. Automatically, that is Canvas. If an assignment is late, it will automatically calculate that penalty. And I'll go in and check it. There's been some question about as to whether it's correct or not, but I'll go and check to see the numbers are okay. But it's 100% a Canvas thing. So if something is due at 11 p.m., then basically at 11:01, Canvas treats it as late. So that begins the first day, then the following day, so on and so forth. So if you think too many points are taken off, shoot me an email. I'll check it out and we'll get it fixed. The other aspect too, if you need to communicate with me, please use Canvas email. I mentioned this before. I have that email on my phone. I get it right away. I would try to get back to you ASAP. The other email, my EDU email, both at Scottsdale and at GCC, I don't view that as much. And plus the Canvas email is the quote official communication method between instructor and student. We have record of all the communication. So do send me your email, your questions through Canvas email. If you're not familiar with that, go to Canvas, far left, there's an inbox, click that, then you can compose an email like you normally would, okay? All right. Any questions, comments, where we're at to date? Let's see, I think I covered everything we needed to talk about. I will then feel free, if you got a question, jump right in there and ask the question. Yeah, got one more person here. So where we were talking about, we were in chapter 6, and we were basically talking about the radius, okay? Now, we had the slide here and that we had in previous chapters, and it's a reminder as to you being able to use a periodic table to determine whether something is a metal, non-metal, or a metalloid. Now, with respect to Chem 130, we're going to be sticking to working with metals and non-metals, okay? So be familiar with whom is a non-metal and who is a metal, because that will assist us down the road, specifically in the next chapter, in determining what type of compound we're working with, which then gives us more information with respect to its properties and so forth, okay? So the radius, basically, that is the distance of the nucleus, from the nucleus to the outermost electron. And I can, hopefully you can see that using the periodic table, you can already determine that. Because let me share the periodic table here, okay? And if we call the numbering sequence, the period is 1 through 7. That also represents the energy levels of where the electrons are occupying, okay? And so it makes sense that if we look at hydrogen, its electron, which is the outermost shell, one of them, is in the first energy level. Now, if we look at number 87, all the way down at the bottom of the column, you can see that it shares with hydrogen the fact that it has one valence electron on the outermost shell, which is occupied in the 7th energy level. So it stands to reason as you go down the periodic table, the elements get bigger. Okay, the elements get bigger. So that is what this is telling you here. Increases as we go down the column. All right, we're getting simply bigger because we got a larger energy level. Now, the difference here, just sometimes it's counterintuitive, is when we go from right to left, left to right. Okay. Now let's go back to the periodic table and let's do a comparison. All right, let me change the color here. And as I stated earlier, if we compare, let's say, lithium with potassium, we can see that potassium's outermost electron is in the fourth energy level. So therefore, potassium has a bigger radius, okay? But what happens when we compare within the same period? So this time, let us raise that, compare potassium with bromine, okay? And so now we're in the same period, we're in the same period, but so we're not going higher energy levels, we're staying within the same period. Now, what they're telling you is this, that as you go from left to right, the diameter gets smaller. And you might think, what's kind of counterintuitive because we're going from left to right, we're picking up protons and electrons as we go from left to right. And you would think that, well, maybe that will make it bigger, but that's not what happens. We find, for example, we compare potassium, which has 19 protons, 19 electrons, with bromine, I circle bromine, which has 35 protons and 35 electrons. Bromine obviously has a lot more protons. We have a lot more nuclear charge, attraction, if you will. There's more positives, protons, which attract those electrons that are out there with a greater force. The result is that bromine tends to pull those electrons in closer, resulting in a smaller radius as we go from left to right, simply because we increased the number of protons within the same period, okay? Going down the period, no problem there. We're getting bigger element. It's obvious that we're gonna get bigger in diameter. Left to right, okay? We increase the number of protons. So there's more positive pull on the negative electrons. And in essence, the effect is it makes the atom shrink in size or radius in diameter. Okay, so one way to look at it to help you out is the snowman here, where the different circles represent the diameter. And so down the periodic table, obviously, diameter or the radius of the atom gets bigger. From left to right, take the snowman, drop it on the side, we can see that the radius decreases, okay? Decreases again because of the more positive pull on the electrons as we go from left to right. So sometimes you're asked the question, why? What's the trend? I mean, don't just give the trend, but explain why it gets bigger in one direction and compared to a different direction, okay? Be specific. All right, so this gives you a general picture, and there's a general trend. Yes, there's exceptions to the rule. Sometimes it doesn't look like it's getting bigger, but the general trend is from left to right, diameter gets smaller, radius gets smaller, and from top to bottom it gets bigger. So you can see that helium, basically helium in the top right corner, is the smallest element that we have with respect to diameter. All right, so maybe ask questions like, which one, given a series of elements, which one is bigger? Well, for example, you're given oxygen, selenium, and beryllium, all right? Well, to answer that question, we first have to find them on the periodic table. We can see here that these three elements are in the same group, specifically group 6A. So obviously beryllium is bigger because it is in a larger radius, it's in a larger energy level, specifically energy level number 5. Okay, so Pe is a bigger atom. Now, if we look at magnesium, silicon, and sulfur, to answer that, we identify them on the periodic table, and I've highlighted them here in the bottom of the slide. Circled them. We got magnesium in the far left and sulfur on the far right. And so the question is, who is larger? The trend is sulfur has a lot more protons, so it's going to pull in the electrons even more so, decreasing its radius. Therefore, magnesium is much larger. Now, another aspect of property we're going to talk about is the ability to pull an electron off an atom. And the same reason here that the radius, as we go from left to right, is smaller, is why it's going to take more energy to remove an electron, because as we go from left to right, we increase the positive negative forces involved there. So it's going to be a lot more difficult to pull off an electron from those atoms on the right of the periodic table as you go from left to right. Down the road, down the group, when we think about it, group number 6, what they all have in common is 6 valence electrons. But Pe, its valence electrons are out in the 5th energy level. They're out far away compared to the other atoms, selenium and oxygen. There's 6 valence electrons in the next energy level in, so they're closer to the nucleus. Therefore, if we needed to pull off an electron, remove an electron, it would be much more difficult to remove one from an atom that has the electrons closer to the nucleus compared to an atom whose electrons are further away from the nucleus. Okay, so keep that in mind because we're going to be talking about this property, which is called ionization energy, and that's the ability to remove an electron. All right, so on the course website, there's some more videos concerning atomic size. You know, obviously, go listen to Dr. Kim Smith. She has her videos concerning this topic and a bunch of other topics, all the topics that we discussed. So you have more resources. All right. So here's what we're talking about this removing an electron. We call that ionization energy. We're making an ion. Remember, when you remove an electron, you create an ion. Now, there's 2 properties here that we gotta make sure we keep separated. This one's called ionization energy, and that is the amount of energy required to remove an electron from a neutral atom, from an element. Okay. The next property, excuse me, is we call En, or electronegativity, and that's I'll define it further down in the next couple of slides, but that's a totally different property. Okay, so don't confuse the two. This is the amount of energy to remove an electron from a neutral atom or an element. So as we go down, and this is the process given to you here in the green, this reaction. We have the sodium neutral atom. Oh, let me get. Okay, we got sodium that undergoes a process where we put energy into the system and we remove an electron. Okay, that's one of the products. We remove an electron, which results in forming an ion. Okay, ionization energy, the amount of energy necessary to remove an electron from a neutral atom. Now, the ionization energy increases as we go up a group, which is what I said earlier, is within the group, what they all share is the number of valence electrons, specifically the A elements, okay? And so group 1A have all one valence electron that they have in common with everybody. So let me highlight those in a couple of examples. So lithium has 3 valence electrons, but one of them is on the outermost shell, specifically in the second energy level. Cesium, number 55, which has 55 electrons, but one of those 55 is an energy level number 6, okay? That is the 1s1 electron, 6s1 electron, and 2s1 for lithium, okay? So they share that common property, but cesium has its valence electron much further away from the nucleus than lithium. And so obviously it stands to reason that the attraction forces of that electron with the nucleus is weaker for cesium than for lithium. Therefore, it'd be much easier to remove that electron for cesium than it would be for lithium. It would take less energy. And that's what they're talking about right here, okay? Now, when we go from left to right, as in the case with the radius decreasing, the ionization increases, okay? For the same reasoning. That is, as we go from left to right in the periodic table, we increase the number of protons and electrons. Therefore, we're increasing the atomic forces involved, the attraction of the positive protons with the electrons, and they're pulling those electrons in tightly, more so than those atoms on the far left, okay, in the same period. Therefore, the energy required to pull one electron as you go to the right increases. Now, the other thing to remember when doing a comparison and looking at ionization energy properties is to remember metals want to lose electrons, okay? Long-term memory, put that in there, okay? Non-metals want to gain electrons. And so if we compare the ionization energy of a metal and a non-metal, we can unequivocally say the non-metal is going to be higher simply because it is a non-metal and wants to gain electrons. And so if we were to compare, let's say, the ionization energy of potassium, okay, which is way on the far left of the periodic table, and we want to compare it with bromine, okay, they're both in the same period, or period, all right, but bromine is a non-metal, and non-metals want to gain electrons, and so they hold on to electrons pretty tightly compared to metals that kind of let them go with not too much energy requirement. And so a simple comparison, the fact that they are a metal, non-metal, you can run it. You don't even have to look them up on the periodic table where they're at. You know that the non-metal is going to take more energy. If we go compare two metals, let's say potassium and calcium, okay, then now we got to look at the number of protons they have. We have calcium has 20 versus 19 for potassium. So there's more force, proton electron force with calcium. They hold on to their electrons a lot tighter than potassium would. So the ionization energy for potassium would be greater, okay? Okay, let's go back. So the result is we get this kind of a graph. And let me kind of explain it here real quick. You can really see the effect of the ionization energy as a function of atomic number. And so on this axis, on the y-axis, we have energy units, okay? Electron volt units, but we just call them energy units. And then in the x-axis is the atomic number, okay? Let me change my color here. Yeah. So if we look at the first element, which is hydrogen, that's that data point right there. I drew the arrow to it. Well, it takes approximately, I don't know, 13.5 energy units to remove an electron from hydrogen, okay? Now, as we move across the periodic table, now we're in helium, and look what happens. Helium's right there, okay? Its ionization energy jumped almost double from that of hydrogen. it's roughly a little bit less than 25, maybe 24.5 energy units to remove an electron. Okay, so we go across the periodic table. We're in the noble gas area. Remember, helium, as far as diameter, is very small. So those electrons are very close to the nucleus, and they're held on pretty tight, much more so than hydrogen. Hence, the energy goes up. Now, wrap it around the periodic table. We start again with lithium, number 2. I got the arrow right there. Okay, look at the ionization energy. Total drop. We're just a little bit above 5 units of energy. And as we progress from lithium all across the periodic table, yes, there's a little fluctuation here and there, but the general trend is when we go across the periodic table and we end up with neon, its amount of energy required is roughly about what, 22 units, 21.5 units approximately, compared to where lithium was at 5. So again, as we go across the periodic table, we're picking up protons, we're picking up electrons, the diameter decreases, the radius diameter decreases, those electrons are held on much more tightly, and therefore when we get to neon, the energy requirement jumps up. And then we wrap it around, we start again in the periodic table, and the trend begins again. We drop almost to 5 again with sodium. And then we go across the periodic table, and we end up with argon. And you can see the general trend again, jump up to about 16 energy units for argon. Now, as we go down the energy levels, the slope does tend to decrease a little bit, change a little bit, but the trend is still the same, where from the far left has X amount of energy, much less energy than to the far right of the column, okay? Eventually, that slope basically kind of evens and flattens out. And it stands to reason, because as we go down the periodic table, now we're down with, energy level number 7, with element number 7. Though the electrons now on the outermost energy level, okay, far away from the nucleus. And then, so it's not going to take a lot of energy to remove them. You can see the trend of the slope of the line basically starts to flatten out, okay? So that kind of demonstrates the ionization energy as a function of atomic number, okay? All right. Okay, so you may be asked questions about, okay, do a comparison like we did with the radius. And the question is here, who has a larger ionization energy and why? Well, let's take a look at these two. We got chlorine, aluminum, and magnesium. Now, I put them in a periodic table, but do I even have to look at the periodic table to answer that question? Okay, I don't. You know why? Why don't I need the periodic table to answer that question? Anybody have an idea? And I got the periodic table. Obviously, chlorine is in the far right. Okay. What we got here? Okay, exactly.
So I have a question. So the ionization energy, it's like opposite to the radius?
No, no,
Like,
no, no. The radius is just the size of the atom.
but like the way that the radius will be bigger on the far left end of the periodic table, and then the ionization energy will be bigger on the upper right, like going on the opposite. I don't know how to explain. I'm confused. Sorry.
Okay, well, let me back it up, but let me answer the question here. So, yes, Christina, you answered that is correct. Chlorine is a nonmetal. I've got a list of atoms, and I want to ask the questions as who has a higher ionization energy? Now you can find them on the periodic table and then search them and then find out their position, or recognize that of these three choices, two of them are metals. And based on what we said earlier, that metals want to give up their electrons a lot more readily than non-metals. And so here, chlorine automatically by default would have the higher ionization energy because it's a non-metal, okay? And it wants to hold on to those electrons and wants to gain them rather than give them up. So they hold on to them much more readily. Okay, so that would answer that question without having to look at the periodic table. But if you forgot that, then you go to the periodic table. So, Christine, you said, so smaller means more energy, and that is correct. Remember, as we, let me put my arrow here. As we go from left to right, okay, the radius gets smaller, okay? With the radius getting smaller, that is because we are getting more protons and more electrons as we go from left to right, which means there's more positive and more negative interactions occurring, which results in the electrons being pulled in closer and tighter, okay? Tighter, which means that if I want to take off one of those electrons, I'm going to require more energy to take them off. Take one out. Does that make sense? All right. So the sideways snowman is another way to look at it. We see the snowman on the side, the radius drops down, which means the ionization energy is higher. Okay. So like you said, I think you asked if that's the opposite. Maybe you can think of it that way. Snowman to the right, the radius drops. Ionization is much higher as you go from left to right, because those electrons are being held down tighter and with much more force than those on the far left of the table. Okay? Does that make sense? Hopefully that answers the question.
Yes, thank you.
Okay, sure. All right, so let me erase that arrow and get it out of the way here. And so chlorine, being a nonmetal, wants to gain electrons and will not lose electrons, but also it is much smaller than aluminum and magnesium. Okay. Now, of the two metals, aluminum and magnesium, aluminum is going to take more energy to remove an electron than magnesium, because again, aluminum has more protons, more electrons interaction than magnesium. So it's going to, the trend goes from left to right, it gets greater. All right. Now, going down the periodic table, we have to find these three elements here. All of them are metals. So we can't use that non-metal metal scenario to help us out. But we realize that they're all in the same group, which means they all share the same number of valence electrons. And so here you got lithium with one valence electron, okay? And I circled the sodium, it's supposed to be potassium. It's okay, and Rb, rubidium, okay? We can see that Rb is an energy level 5. So its valence electrons is in the 5th energy level. Potassium is in 4th energy level, and lithium is in the 2nd energy level. That is the valence electron. Okay, so you know it's like I'm sitting here, and I am lithium. Well, my valence electrons may be 10 feet away. Okay, so now I'm potassium. Maybe my valence electron is maybe 30 feet away. And now I'm Rb, and my valence electron could be maybe 100 feet away. And so my interaction with that electron 100 feet away is much less than my interaction with the valence electron maybe a few feet away, like lithium. And it's smaller, so it's holding on tighter. So that being the case, lithium, because it's smaller, holds onto its electron tighter than the larger atom. All right. So in Again, on the website, there are some more videos concerning ionization energy. Feel free, obviously, to go and view them, get some more detail, to get additional detail. Which brings us to this property, and we're almost done with the chapter. And this is very, very important because this really is going to be used quite a bit when we start talking about bonds. We start making bonds, and this really has an effect on the properties of the molecules that we work with, okay? And this property is called electronegativity. All right. So, and we were talking about the ability of an atom to attract bonded electrons. Now, what do I mean by that? Okay. We're going to learn here. Let me pull something up. We're going to learn. I'm going to draw it by, I'm going to say I have carbon, and I draw a hyphen and a carbon. Okay. What that means, that hyphen represents 2 electrons. And there is a bond between these 2 electrons that are being shared. Okay. There's a bond between the 2 carbons, I should say. And that hyphen represents 2 electrons. So I could write it with a line, or I can write it with 2 dots. 2 dots, again, represent a bond. So either way is correct to write. We tend to write lines. It's just quicker to write. You know, if I had the board, I can be writing them on the board very quickly instead of doing double dots each time. Okay. Now, here's the difference. We're going to learn that there are 2 types of chemical bonds. There's a type of bond where ions are attracted, and they're basically 2 magnets, if you will. I got a positive ion like sodium with a full-fledged positive charge, and then I got a chloride ion with a full-fledged negative charge. They come together and attract each other. They don't share anything. They attract each other because of the full charge that each one has. Positive attracts the negative, okay? And that is one type of bond that we're going to learn. We're going to call, that's going to be called an ionic bond. Those crazy bonds, they don't share anything, okay? Now, another type of bond is like this carbon-carbon bond. There is a sharing. And my fingers represent 1 electron on each hand. And they come together and they literally form a bond where they share those 2 electrons, okay? So when we talk about electronegativity, this is what we're talking about. That one of these atoms has a tendency to pull those electrons, attract them onto itself much greater than the other one. And that is related to what we call electronegativity. So if an atom has, in a bonded situation, if an atom has higher electronegativity, it has a tendency to pull the electrons in that bonded pair. It is similar to a tug of war. It is analogous to a tug of war. I get 200-pound two people that are 200 pounds apiece, equal strength. They are doing a tug of war, pulling the rope, right? 200 pounds. Well, 200 pounds here, 200 pounds here, pretty much a stalemate, okay? It's an equal pull here, equal strength, everything's the same. There's no pull one way or the other, no advantage. Now, take that 200-pounder, exchange it for a 400-pounder. And now we got a 200-pounder and a 400-pounder pulling. Who's going to win the pull? Obviously, the 400-pounder has got more weight. And the electronegativity is that type of scenario where they're sharing the electron. But if I got an atom that has a higher electronegativity, it's analogous to putting in a 400-pounder, it's going to pull those electrons onto itself. And what results in is a total change of properties with respect to compounds. And we end up with a bond that we call a dipole. We're all familiar with dipole. We live on a dipole. The Earth is a dipole. 2 poles, di meaning 2. We got the North Pole and the South Pole. All right. Your battery on your electronic device is a dipole. You got a positive and a negative, 2 poles. And so compounds also have that. We have a dipole. And that's a result of this property called electronegativity. And it's pulling the electrons, kind of stripping the electrons away from the other atom, not 100%, but just leaving them with a lot less electrons than the one that's pulling it. Now, fluorine is the most electronegative element that there is, as far as measuring their electronegativity. Okay, so I'm going to type it right there. And we use that as our benchmark to compare the electronegativity of other atoms. For example, let's say I have a bond between carbon and nitrogen, which there's many bonds like that, carbon and nitrogen bonds. And we want to determine which one is more electronegative. Well, we come to the periodic table, we find how they are related, how are they positioned relative to fluorine. So in this case, nitrogen is a lot closer to fluorine than carbon. So in this scenario example of a carbon-nitrogen bond, the nitrogen will be a lot more electronegative, and therefore that bond would tend to pull the electron density toward the nitrogen. The same is true if we were to compare a nitrogen and an oxygen bond. Oxygen is much closer to fluorine, therefore it's a higher electronegative. It has a higher electronegativity, oxygen does, than nitrogen. Therefore, if there were a bond between nitrogen and oxygen, which there are many examples of, the electron density, if you will, is pulled toward the oxygen. Okay, so we use fluorine as our little benchmark because down the road we're going to be comparing the electronegativity of bonds. Okay. All right. So that's electronegativity. Now, noble gases don't have no electronegativity, because again, they're noble gases. First of all, they don't form bonds. They already have an octet. They're fulfilled because, well, helium is a duet. Remember, helium has a duet rule. Does not have eight electrons. But everyone else, all the other noble gases, that's in group 8A, okay? They don't make bonds. And for 10-130, they do not make bonds. But the big boys down the road, they can make some stuff, okay? But for us, they don't make bonds. All right. So with that being said, that's the end of chapter 6. We're a little bit over than 1/3 of the chapters, right? Almost. So electronegativity, this is a very important property. Be familiar with this. We're going to come back and use it when we start talking about chemical bonds, and then we're going to actually use it to determine the properties. Okay, the properties, because that dipole in a molecule really has a big effect on what we call polarity. Okay, now, and well, what does that mean? Well, let me give you an example. All right. I'm told that there is some hurricane-proof makeup out there, right? That you put it on and you can survive a hurricane because the water will not take it off, right? And then I also know there's makeup out there that washes off with soap and water. Well, that hurricane-proof makeup, you require something, like some oil to remove, right? It's a non-polar solvent to remove, as compared to soap and water, which is polar. And all that's related to the polarity of the molecules and who's carrying more electrons than the other, which causes a change in properties. We'll be using that polarity to determine and that interaction and the electronegativity to determine how we can do a relative comparison. Would this be more soluble in water, or would it be more soluble in oil? We all know that oil and water do not mix. Don't believe me? Get some Italian dressing, right? You got two layers. You got the oil layer and the aqueous layer. They don't mix. You shake it up, they're not really mixing, they're forming an emulsion. But they don't mix because of polarity. Like dissolves like. If you want something to dissolve, you find the polarity of that material and you treat it with something with similar polarity. Okay? But a lot more on that when we get going with the other chapters. All right. Any questions so far? No? All right. So we're done with chapter 6. We're going to get into chemical bonding. Now, there's tons of chemicals out there. We got billions and billions of different chemicals. And all these chemicals out there, there are only 2 types of chemical bonding. Only 2 types, okay? We're going to learn about this. Now, the other thing we're going to learn about how chemicals have a geometry. They have how they are in space 3-dimensionally, what's their structure. Okay, we're going to learn how to do that. So, but we're going to use the shapes table. If you haven't downloaded that shapes table, do download it because we will make lots of reference to it. Okay, that's the shapes table here. Now, notice the shapes table has 4 columns. Now, the first column, I'm going to highlight that, is a what we call a general formula. Okay, and like it states, it's a general formula. We are going to be looking at, we'll be given a compound, okay, and from the compound that we're given, you're going to always be told who the central atom is. Now, what happens is we have a compound which is made up of more than two different elements. There's always going to be one that is a central atom, and everything is bonded relative to the central atom. Okay, and that atom we're going to designate in the general format as A. Okay, so A, notice all the different general formulas we got there. There's only going to be one A, and that is the central atom. Now, B would represent whatever is bonded to the central atom. They could be the same element or they could be different. It makes no difference, okay? So in the first example, you can see we got an A, B subscript 2. There's 2 Bs. That means that A is in the middle, that's the central atom, and then we got 2 Bs bonded to the central atom. That's it. The other general formula is the letter E. Okay, what E represents is what is called lone pairs. Now, once we're given a formula, we're going to go to the periodic table and determine how many valence electrons each atom brings to the structure, to the formula, to the compound. Okay, we're going to use the valence electrons of each atom to determine the type of bond and how many bonds this molecule is going to have. And what happens is sometimes depends on the atom, but I can tell you right now, those in group 5 will always have what we call a lone pair of electrons in the central atom. So nitrogen and phosphorus will have a lone pair. Oxygen group 6 will always have 2 lone pairs. And we designate those pairs by 2 dots. Okay, you can see right here, 2 dots. And there's like a little shape, it represents an orbit. Okay. Now, a bond, like I was explaining earlier, we designate by a line. So you can see the central atom here, A, whatever A may be, this is A right there. And then we got B attached to A, and there got another B over here attached to A, okay? So on the central atom, because of the valence electrons we're going to work with, we're going to have maybe one pair on the central atom. And that is what E is, okay? The B's could have other lone pair of electrons, but we don't care about those. We only care about the central atom. We're going to learn how to put these together. Keeping in mind the octet, because everybody has to maintain the octet, 8 electrons around it. Those 8 electrons could be either shared with someone, another element, or they could be on their own, like this lone pair. Okay. So sometimes you have 2 lone pair. We got that one here and that one here. 2 lone pair on the central atom. All right. So let me erase all this so we know what's going on. So A is the central atom. B is whatever element is bonded to the central atom. And E represents any lone pair that's 2 electrons on the central atom only. Okay. So given the formula that we have, we're going to come up with a general formula. And then we're going to take the general formula, and that's going to give us more information. So if we come up with a general formula of, let's say, AB4, based on the compound that we're given, we come up with a general formula, and that means we've got A as a central atom, which could represent carbon, and then we got 4 B's around it, which could represent hydrogen. This is the most common geometry that we find in nature, and that is called tetrahedral. Okay, where we have a central atom. What is the half circle mark? Are you talking about where the 2 darks are, Christina? Yes, that half circle mark represents an orbit. Okay, it's always saying it just represents an orbit. It just says that occupies an area with 2 electrons. Okay, and so the most common general formula that's out there is this species with 4 atoms attached to it in the central atom. We call that tetrahedral. And that has a specific bond angle. And that bond angle is right there. And that is the angle between whatever's attached to the central atom. Okay. And that bond angle is 109.5 degrees. Notice the lines. I don't want to put too many arrows up here. It gets a little crazy. But the lines, remember something, that line represents a bond between the central atom and whatever B is, between A and B. Okay, there's a bond. There's 2 electrons in that line. And the being electrons, that configuration, there's 4 bonds around the central atom with electrons and negative charge. So they're going to automatically put themselves in a 3-dimensional in space. They're going to maximize their distance from each other because they're going to repel each other, right? And that is the ultimate configuration, if you will, of those lone pairs, of those pairs of electrons, those 4 pairs. And we call that tetrahedral. Now, what happens is that half circle right there, that in those 2 dots, those are 2 lone pair of electrons that exist in the central atom. And that half circle, it just kind of demonstrates that they take up quite a bit of space. Okay, because there's 2 electrons, it's like an orbit. Basically, it is. It's an orbit, like the p orbit. And there's 2 electrons in there. Well, being 2 electrons, they repel each other. They're now bonded. Okay, remember, they're now bonded. They're called lone pair. They're now bonded pair. If they were bonded pair, there'd be a straight line between 2 atoms. Here, it's just a lone pair. They tend to occupy more space. And the result is that bond angle between the B's gets shrunk. Okay. One would expect to have a shape like this one here. Okay. But because those electrons, so linear is considered lone pair? No, not quite. No. There's no lone pair on the linear configuration. We'll come back to that in a second. Okay. And so because those electrons occupy more space, they shrink, they collapse that bond angle, and that's why we have a less than 120 degrees. We would think, like the AB3 model, we have 3 atoms bonded to the central atom, everybody distributes themselves equally. We would have a 120-degree bond angle, which has the name trigonoplanar. But because those lone pairs occupy more space, that bond angle gets crushed, okay, and gets smaller than 120 degrees. The same is true for AB3E, where we have a lone pair in the central atom. We would think, like the tetrahedral, we will end up with 109.5, but those lone pairs occupy more space, and they crush that bond angle right there, causing it to have a bond angle that's less than 109.5, like the tetrahedral. And that has its own special name. That is called trigonopyramid. That is 3 things attached to the central atom with a lone pair. And then we have an example of what is called bent, where the central atom has 2 lone pairs. And the classic example of this one would be water. We're going to draw this where these lone pairs are. Water has 2 lone pairs in the oxygen and H2O. So here you got the 2 hydrogens could be this. These 2 have highlighted. And then the oxygen could be it would be the central atom. So, and then the lone pair on the central atom. Okay. Too many arrows. Let me clear it up a little bit. Now, with respect to linear, which is this one up here, we have a formula where we have A, and then there's B2. There are 2 moieties, 2 other atoms bonded to the central atom. Okay, that gives us what is called a linear configuration. There's no lone pairs involved here. Okay, no lone pairs at all. But because of the way the structure is, it's a linear configuration, and that bond angle is 180 degrees between the B's, or whatever's attached to the central atom. Does that answer your question you had, Christine? Okay. All right, so we get this table printed out and be ready to use, because we're going to be given the formula. From the formula, we're going to determine the valence electrons that we have, add them all up. We're going to be given who is the central atom, and then we're going to put all the other things attached to the central atom. Keeping in mind, we want to maintain the octet rule, keeping 8 electrons around an atom. And then we come up with the general formula, which gives us the geometry, the molecular geometry, which then gives us the name of that geometry, the name of the shape, which then gives us the bond angle. Okay. All right. So we talked about this at length, and I can't overemphasize. The goal here is to have 8 valence electrons, or the octet rule. Hydrogen and helium have the duet rule. Okay, so hydrogen is a good point here. Hydrogen will always have 1 bond. You will never see 2 bonds on hydrogen. Always 1 bond. Okay, because it only has 1 electron. And helium, obviously, you're not going to see a bond to anything. Okay, and because it's part of the noble gases. So that means that everything else we're going to work with has to have 8 electrons around it. And those electrons could be either shared with another atom, or they could be lone pair on them. Okay, as long as they fulfill 8 electrons around it. We talked about metals want to gain electrons, so we got cations. Non-metals become anions because they want to gain electrons. Now, how do we determine the 2 types of chemical bonds? Well, number 1 is this. When you have a combination of a metal and a non-metal, okay, a metal and a nonmetal. When you have that combination, that is an ionic bond. Okay, we have a full-fledged positive charge and a full-fledged negative charge. They come together like two magnets. They attract to each other. Now, what happens with ionic bonds, when we put them in water, guess what? They break apart, and they break apart into their ions. For example, if you were to um, fill your bathtub up with pure 100% water, okay, you can throw your plugged in electric dryer in there. Nothing is going to get, there's going to be no electricity is going to, you'll be safe, okay, because there's no ions in the water. Now, the moment you touch a little pinch of salt, throw it in the tub, you form ions. Now those ions are the ones that conduct electricity. Ions or electrolytes, you know, you're out working out, you got to drink electrolytes. What you're doing is you're drinking the ions or these elements that have gain and loss in electrons, okay? Because those guys are the ones that are carrying the electrical charge in your body and so forth. Anyway, so the periodic table to determine who's a metal and who's a non-metal will be important here, okay? Because once you know the combination, metal, non-metal, you know it's an ionic bond. With respect, all right, well, let me, before I proceed with the next one. When you have an anion and a cation, when you make an ionic bond, it is only a combination of the cation and the anion. Okay, you cannot make an ionic bond with two cations or two anions because they repel each other. The cation, which is positive, and the anion, which is negative, attract each other. So calcium, its partner, if we're going to make a compound, will be the bromide, not the lithium, okay? Because the bromide has a negative charge. It is the anion. So cations, again, ionic compounds are made from metals and nonmetals. Metals lose electrons, become positive. Non-metals gain electrons, become negative, okay? All right. So other examples would be like KCl, which is called potassium chloride. And then we got calcium bromide, okay? Is an example there. Now, the other type of compound that we're going to work with, let me change the color a little bit so there'll be no confusion, is a combination of a metal and a non-metal. Excuse me, a combination of two non-metals. I had ionic bond in my brain. Two nonmetals brought together, okay, to give you what is called a covalent bond. They are covalent compounds, okay? Now, in this scenario, they are truly sharing electrons in the bond. Earlier, I was showing you in the shapes table that line represents a bond. I gave you an example of a carbon-carbon with a hyphen between them. That represents a bond where these electrons are being shared between two atoms. They're not total, they don't separate, they're being shared. Now, the sharing could be equal sharing, like the 200 pounders pulling that rope, or it could be unequal sharing, like the 200 pounder and the 400 pounder, which is related to the electronegativity, okay? Where you get equal sharing and not equal sharing. All right, so the difference between the two, covalent and ionic bond, if I were to take a covalent bond compound and put it in water, it does not break up. It does not break up into the ions like the ionic compound. It stays intact, okay? So we have things like all the diatomic elements, H2, nitrogen, hydrogen, fluorine, chlorine, you know, they're sharing electrons to make a bond, okay? And then you can have things like water, H2O. Hydrogen is a nonmetal, oxygen's a nonmetal. Two nonmetals, that is a covalent compound. They have covalent bonds. Then you have carbon dioxide. We got carbon and oxygen, right? Two non-metals, carbon dioxide. These species, when they go in water, do not dissociate. Ionic compounds dissociate. Some of those ionic compounds dissociate 100%, some maybe 5%, but nevertheless, they dissociate. Okay, they break apart into their respective ions. So that is the two main types of compounds that we have. That's it. Ionic compounds and covalent compounds. And underneath the covalent compounds, when they're sharing, there's going to be equal sharing or not equal sharing. So for example, all the diatomic elements like hydrogen and nitrogen and fluorine, there's two atoms, but they're the same. So with respect to electronegativity, this is where electronegativity comes into play. Those two have the same electronegativity, two hydrogen atoms, two nitrogen atoms, or two fluorines. Therefore, that bond is equally shared. And there's no tug of war going on there. You got the two 200-pounders pulling on that rope, okay, equal sharing. On the case of H2O, you have a hydrogen and an oxygen bond, okay? Well, now you have two different elements here and two different electronegativity values. And so the oxygen being more electronegative than hydrogen will tend to pull the electrons onto itself, more so than the hydrogen will, and kind of stripping the electrons away from the hydrogen, causing a partial positive side. It doesn't get rid of it, okay? But it creates a partial positive side. For example, and this is important here. How many have taken a balloon? I wish I had one here. I thought I did. Rubbed it on your head, okay, and then put it on your chest. What happens to it? Does it stick? Yeah, it sticks, right? Yeah, it does. No. Why? Is it from Harry Potter magic? Why does that balloon stick to you? You ever thought about that? I'll tell you why. All right. Wake up in the morning, your hair's like, okay, you got a bad hair day. Your hair's all crazy. It's all staticky, and you can hear the electrons in your hair, right? You get that balloon and you rub it on your head. What you in effect have done is transferred some of those electrons onto the balloon. Okay. Now, the balloon now has electrons that have a negative charge. Okay. They have a negative charge on there. Now you bring it to your chest. Now on the surface of everything around you, everything, there are electrons. Okay. Anything you touch, anything you grab, you really, truly don't really grab that item. You really are touching the electrons that item has, and they repel each other. Yes, the mechanical forces are strong enough to overpower it, and you're holding on to it, but you truly don't really hold on to that item because there's a separation down in the atomic scale. So anyway, you bring that balloon towards you, and on the surface of your body, you have electrons, which have a negative charge. And as you bring it closer to your body, those electrons get repelled on your body, repel, and essentially move into you. When you do that, you leave a positive nature to the surface of your skin, of your body. It's more positive because less electrons are there, becomes more positive, pushing because those electrons are being pushed into your body. And so now here comes the balloon with a bunch of negative charges. Now they're attracted to the positive area of your chest and they stick. Okay. It is forced. You created a dipole. You generated a two pole system, negative pole and a positive pole. Okay, and that's that's what's kind of happening with the hydrogen and the oxygen. Because of the electronegativity, you actually create a permanent dipole. The balloon, you form a temporary dipole because you know that balloon's not going to stick there very long. It's going to fall off eventually. It's because it goes back to its ground state, its more stable state. But with respect to bonds, you create a permanent dipole, and so on one side it's going to have a positive nature to it, on the other side it's going to have a negative nature to it, and we're going to have a lot more to say about that. It's all related to electronegativity. All right, so now, so we got two types, ionic bonds and covalent bonds. Okay, so we're going to start talking about ionic bonds first and how to put them together. Now, the thing about putting compounds together is this, especially ionic bonds, is that, first of all, point number one, you put the cation and ions together, okay? Two positives are not going to come together to make a compound. All right. Now, the second part is when you put them together such that you have sufficient positive cations and sufficient negative anions to cancel each other out to end up with zero. Okay. For example, you have the formula written here, calcium bromide. Now, how do we know for sure that that is the correct formula? Well, first of all, we recognize this is an ionic compound. Why? Because calcium is a metal and bromide is a nonmetal. Okay? So why is that formula correct? Well, what do we know about calcium? When calcium becomes Ca, when calcium becomes ionic, okay, what is calcium's charge? It is a +2, right? Calcium is in the group 2, is element number 20. It is group 2, and that's why it's so important to learn these valence electrons, okay? Because you could be given a question like, what is the formula for calcium bromide? Just in names, calcium bromide. Well, from that information, you need to figure out, well, okay, I got to figure out what the formula is. Well, you first break it down into ions. Calcium, ionic calcium. I got to find it in the periodic table. It's a metal, so it's going to lose electrons, and it's in group 2, which means you're going to lose 2 electrons, resulting in a +2 charge. Okay. Bromide is a group 7. Now, bromine is a group 7. When bromine becomes an ion, we change the name to bromide. It picked up 1 electron. So we know that bromide has 1 negative charge, -1 charge. Okay, you can just put the negative or you can give it the -1. It makes no difference. Okay, so I put these guys in ionic form. All right, now I got to put them together such that the negatives and positives cancel each other out. So I only have 1 negative bromide. So that tells me that I need 2. Each one is a -1 charge, but I need 2 of them to cancel the +2 charge from calcium. So I got a 2 in front of bromide. Okay, where that 2 becomes the coefficient, the subscript in the formula CaBr2. Okay, because I need 2 of it. Calcium, normally when elements are written out, calcium is written first. And you'll find that the metal part for ionic compounds, the metal part is written first, given the name or the formula, then followed by the negative part. So Ca is written first, then followed by Br2. Okay. Now the thing is, well, how do I know that's not bromine, diatomic bromine? Well, here's why. because the way it's written, calcium is written first. That tells you if Br2 was coming following the calcium is attached to calcium. Okay. So that's not diatomic bromine. If it was just bromine subscript 2 written all by itself, then yes, that would be the element bromine. Okay. All right. For covalent compounds, as a general guideline, 99% of the time, the first atom written is the central atom. Okay. There are exceptions to the rule. Not many, but the majority of the time, the central atom is written first. And the same is true for the ionic compounds. The central atom, which is the metal, is written first. All right. So, and that explains why it's not diatomic. We just talked about that. All right. So you may be given a list here, and you said, okay, which compounds are ionic? So you got a list here. Well, and you have to define. Well, you might forget. Well, what do you mean ionic? Well, go back and refresh your memory with respect to how an ionic compound or ionic bond is defined. And it is defined that is a combination of a metal and a nonmetal. And you forget what the metal and nonmetal is, then I refer you to the periodic table because you can use that stair step. Anything to the left of that stair step are metals, except hydrogen, which is in the far left, and things to the right of the stair step are nonmetals. Okay. All right. So by looking at this list, we can see we got KBr. So what do you think about KBr? Do you think that's ionic? And yes, KBr would be ionic because potassium is a metal. All right. All right. So we can highlight that. We'll highlight it. So that's ionic. We got that on the list, which, by the way, its name is potassium bromide. All right. The next one, SO3. There's a sulfur, and then there's 3 oxygens bonded around that sulfur. Its name, it is covalent. That is correct, Christine, because we have sulfur and oxygen, 2 nonmetals. Okay, 2 nonmetals. That is called sulfur trioxide. We'll come back to that in a minute. And now, how about HCl? That's what's roaming around in your stomach right now. Hydrochloric acid, tons of it. You know, if you eat too much Taco Bell, you get too much hydrochloric acid. So think about this. This hydrochloric acid, if you eat something that doesn't settle well, kind of acidic, and what do you take? Pums, right? Pums is calcium hydroxide. Okay. Pums is a base. You got acid in your stomach. You have one of the chemical reactions occurring in your belly. It's a neutralization reaction, of which there's only 6 types of chemical reactions we're going to talk about. So yes, HCl, is that ionic or covalent? I got covalent, yes. Why? Hydrogen is a gas, it's nonmetal. The chloride is nonmetal. Okay, both nonmetals. That is covalent. HCl is a covalent compound. Br2, bromine, 2 nonmetals, covalent. Okay, carbon dioxide, CO2. What do you think CO2 is? Covalent, exactly. Carbon and oxygen, 2 nonmetals. And then finally, we got the last one. That is magnesium chloride. Definitely ionic, right? Because magnesium is metal, chloride is a nonmetal. So of this list, we have only 2 compounds that are ionic compounds, okay? Now, as I said earlier, ionic compounds, if I put them in water, they will dissociate into their respective ions. So if I took potassium bromide and I just dumped it in water, it would break up into the potassium positive and the bromide negative. The same is true for magnesium chloride. That also what break apart to give you the magnesium ion and the chloride. In fact, that's magnesium chloride is used a lot for flavors in your water. Some of the water that you buy, uh, like smart water, they distill it, purify it, then they put magnesium back in there for flavor. So, okay. Now, the other guys don't do that except for one. And these are acids, HCl. Uh, HCl is a covalent compound, but when we put it in water, it dissociates into the respective uh, uh, ion, so H plus and chloride. But those are the only exceptions to covalent compounds that break up into ions, okay? And we'll talk about that when we get to the acids and so forth. So I'm going to introduce you to the name here. So potassium bromide, okay? We call that potassium bromide, not bromine, because we are working with the ionic bromine, okay? SO3, this is sulfur trioxide, okay? Sulfur trioxide. Now you're going to be noticing the naming here is we start putting prefixes, but only for covalent compounds. Like the bottom one, magnesium chloride, we just call it magnesium chloride. We don't call it magnesium dichloride, but only covalent compounds use prefixes. So sulfur trioxide. You probably may have smelled this one. This is part of the, sometimes you're in front of a car and you smell this rotten egg smell from the exhaust of the vehicle in front of you. That's what you're sniffing. Sulfur trioxide. Sometimes it's an exhaust gas from our combustion of our fuel. That gets up into the air, reacts with water, eventually forms sulfuric acid, another strong acid up in the atmosphere. It rains, drops back down, causes all kinds of problems. This one, depending if it's in water, is called hydrochloric acid, or if it's in water, hydrochloric acid. If it's an aqueous solution, or it's just called hydrogen chloride. Okay. And if it was a water solution, they would have the parentheses AQ, meaning aqueous solution. Okay, so then its name would be hydrochloric acid. If it's a gas, it's hydrogen chloride. Okay. Then obviously you got Br2, which is bromine, just simply bromine. Okay. And then we got CO2, which carbon. Dioxide. Okay. Notice we use the prefix di to show we got two oxygens. If this was one oxygen, it would be called carbon monoxide. Okay. And then finally, the last one here is magnesium chloride. Now, you might be tempted to say dichloride because they're two, but again, for ionic compounds, there are no prefixes. Only the covalent compound has prefixes. Okay. And if it's just a diatomic element, it's just simply bromine. It's not dibromine, nor dichlorine, nor diiodine, just iodine, bromine, chloride, hydrogen, all the diatomics, just their single name, no prefix di. Okay. And I enter these names here because I'll be doing it as I go along, because there is an exam that SCC wants everyone to pass. You got to pass at least by 80%. That's that nomenclature. Now you have an infinite number. Well, no, not infinite. You have a numerous attempts to take that exam. It's a list of 20 questions. It will either give you the formula or the name. So if you got the formula, they want you to give you the name. If you got the name, they want you to give you the formula. Okay, it's called the nomenclature exam. Now, what I'm going to do in the grade book, I'm going to set everything to 0 because right now that grade is not incorporated into your overall GPA, okay, because it's blank. And so sometimes it gives one a false idea of what the grade is. So to demonstrate what effect it can have on your grade if you don't pass it, I'm going to put a 0 in the grade book. Now, what happens eventually when you pass 80%, it will, or keep it at 80, whatever percentage above 80 and 80, it will stay. Anything below 80 gets changed to 0. And so it's going to demonstrate how that particular assignment can have could have an effect on your grade depending if you're on the border. You know, if you're on the border, it could drop you down. Okay. So don't get too frightened and shook up when you see that change, but that would definitely give you an idea as to what your grade really is if you don't pass the nomenclature part. Okay. Is it correct to label any of the diatomic elements with N or N2? The N, if it's a diatomic element, you have to write it as the subscript 2. Okay. Subscript true if you are trying to demonstrate if you say if it's written, let's say write the reaction, and you read this and it says write the reaction of sodium plus chlorine to give you sodium chloride. If you were to see that written out, you need to convert that to an equation. Then that chlorine, you have to remember, is diatomic, so you will be Cl2. Okay. BCl to all the diatomics, have no fear of ice cold beverage. Always will have the 2 in there. Okay. All right. So here's the name for a lot of these compounds. Now, so I'm going to, as we proceed and we start working with these, I'll be introducing the name and get you going. We're going to have a whole chapter in nomenclature, but you can get started in this. Also on the website, there is a study guide to help you with respect to naming. I uploaded 140 compounds and you can do flashcards. And so click on it, help you start naming the compounds, okay? All right. So, yes, Eric asked a question, would it have questions like cupric and cuprous, ferric and ferrous? The answer is no, because that nomenclature, the ick and the us is no longer, well, I shouldn't say no longer being used. We'll be using Roman numeral to describe what is the charge of the metal. So you won't see cupric or cuprous, but you will see Roman numerals 1, Roman numeral 2, Roman numeral 3. When we get to that, we'll talk more about that. Yes, because there's the naming cupric and cuprous is very ambiguous. And what that does is demonstrate, it shows the metal and what charge it is. Remember, the B elements, we cannot really predict the number of valence electrons and their charge. Iron, for example, could be a +2 or +3. Copper could be a +1 or +2 charge. And in the old nomenclature naming, they would call it the cupric and the cuprous, and that became a little bit ambiguous. So what has been done is to remove that and use Roman numerals and parentheses to describe the actual charge. All right, but we'll get to that. So you won't see the cupric and the cuprous. All right, so that's introduction to naming here. Let's clear this out. Good questions. Tell you what, you guys, let's take a little short break. I just noticed the time is 2:30, and let's pause the recording for a little bit. Hey, so quick rehash on this particular slide here is basically which compounds are ionic. Remember the definition of ionic bond / compound, and that is a combination of a metal and a non-metal. So these, the first one, potassium bromide and magnesium chloride, are ionic compounds. The others are covalent. Okay. Ionic bonding. The key about the type of bond is that there is a complete transfer of electrons from the metal to the non-metal. Okay, a complete transfer of electrons. Furthermore, a full-fledged charge on the corresponding ions that have been created. For example, we got sodium ion, full-fledged charge. The chloride ion, full-fledged negative charge, okay? And the fact that they're positive and negative, they attract to each other to form this interaction between the two, which is not a bond. We call it a bond, but it's not a true bond. It's a attraction and electrostatic attraction between the two. So, and that's electrostatic attraction / bond, okay? Because of the respective resulting charge that they have with each other. Unlike the covalent bond, where we are truly having sharing a true bond between the two atoms. So here we have an example of the sodium atom reacting with the chlorine atom, okay? Now, Christine, I think you had a question earlier when you said chlorine, this should be subscript. Well, yes, normally it's a diatomic, so you will write it Cl2 unless I ask you the chlorine atom. Now, the electrostatic bond, similar to the balloon, exactly. Yeah, but with the balloon, it's temporary attraction. Here, because the full-fledged permanent plus charge or permanent negative charge, that's a permanent electrostatic attraction. Yes. So if we also, the other thing to look at, as I was saying here, they're asking the chlorine atom. So here we can write just one chlorine atom because we're talking about specifically about a chlorine atom. If they talk about a chlorine molecule, then we're talking about Cl2 subgroup 2. Okay. And we can notice the color for the sodium is that, I guess, purple color from my screen. And that diameter represents the diameter of the sodium atom. Okay. It loses that electron. Remember, sodium's got one valence electron. It loses that one valence electron. So now it starts off in group third period, 3s1 for that one lone electron. When that's empty because it loses it, then the next energy level comes into play, the second energy level. And so its new diameter is smaller. So you can see how the color change, the size has drastically changed from the atom to the ion by losing an electron. And the converse is true for the nonmetal, where the chlorine atom, being in group 7, has 7 valence electrons. It's a nonmetal. It's going to pick up an electron. It's going to pick up specifically the electron the sodium atom has left, and the results in the diameter of the ion, the chloride, is much larger. Okay. And so that really kind of demonstrates what happens to the radius when the atoms become the ions. It's a good visual. Okay. And then you have what's happening here with respect to the salt, in this case, sodium chloride. Now, the term salt, I know you may think automatically table salt, sodium chloride, but with respect to chemistry, a salt is literally any ionic compound that forms a bond, if you will, ionic bond with a metal and a nonmetal is considered a salt. All right. So the corresponding salt is very structured, very ordered. And if this salt is dissolved in water, then what happens is those ions break apart, completely break apart, and go into solution. Okay, into their own respective ions. Compared to covalent compounds that don't do that, with one exception only, one exception. Those are the covalent acids, like hydrochloric acid, phosphoric acid. We'll talk about those. So those are the only exceptions that of covalent compounds that break up into ions. All right. So we talked at length about this with respect to loss of electrons. We know that the magnesium ion, when it becomes an ion, when magnesium atom becomes an ion and loses 2 electrons, now has a +2 charge, it now has 10 electrons, and we have to put a subscript, which reminds me, when you're doing the electron configuration in these questions, be aware there is a difference in the electron configuration of the magnesium ion versus the magnesium atom, okay? The magnesium atom has all electrons. The ion does not. It had lost some ions. In this case, it lost 2 ions. So its electron configuration is completely different, okay? And the same is true for the anion. The sulfur electron configuration is much different than the sulfide electron configuration. So when you read the question, take a look, make sure you're talking about the element or you're talking about the ion, okay, with respect to electron configuration. And so in this case here, we got these electrostatic forces that bring these together. And the fact is, magnesium has a +2 charge. The sulfide has a -2 charge. Okay, so we can put them together on a 1-to-1 ratio. So if we were to write a formula for magnesium sulfate, it'd be simply MgS. Okay, MgS. Oh, let me get rid of it. Recap on the ionic size. We talked at length about this. Cations lose electrons, and now we have more protons, and obviously now they're going to be smaller. Plus, they lost the outermost valence electrons. So next valence shell is the next one in, and converse for the anions with respect to their size, their radius. So you may be asked some questions, some true and false questions. And the question here says, the aluminum atom loses electrons and the iodine atom gains electrons. What do you guys think? True or false? The aluminum atom loses electrons and the iodine atom gains electrons. And that would be true. True because aluminum is a metal and all metals want to lose electrons, and iodine is a nonmetal, and all nonmetals prefer to gain electrons. Okay, true statement. So the aluminum atom is larger in radius than the aluminum ion. What do you think? True? Okay, we got one true, one false. Give us some thought. So we got the aluminum. That's a true statement from Christina. Yeah, think about it. Think it through now. We have the aluminum atom. All right. Aluminum is number 13 on the periodic table. It's in group 3, so it's 3 valence electrons. Also, it is in the third, okay, so it'll be 3s2 and 3p1, those 3 valence electrons, okay? Now, when it's a metal, so it's going to lose those 3 electrons. And so now the next valence shell will be in the second energy level. So again, it lost 3 electrons. Now the radius now goes on to the second energy level. Plus, it has more protons than electrons. So those electrons are even pulled even tighter together than before, so that the radius gets small. So it's a true statement. Okay. The iodine atom is smaller in radius than the iodide ion. And this would be a true statement because this is the converse, the opposite of the metal, because now it's picked up an electron, okay? Picked up an electron and now it got bigger. If you forget, look at the previous slide, this one. Look at the sodium, the diameter of the sodium atom compared to the diameter of the sodium ion, okay? Where it lost an electron. And then look at the diameter of the chlorine atom as it becomes the chloride ion, okay? It picked up an electron. One more electron in its valence shell, takes up more space. Okay, so we got true, 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 and true. And finally, okay, the aluminum and the iodine ions form a bond by attraction. And that, ladies and gentlemen, will be a true statement because we have a full-fledged positive and a full-fledged negative charge. And like two magnets coming together to attract each other, that's how they come together, okay? And we call that an ionic bond. Not to be confused with a covalent bond, okay? Now, with respect to metals, there's not much we're going to say about these. It's just basically that all metals are good conductors of electricity, and they being good conductors, they're good conductors of heat, but they're loaded with electrons throughout the surface. The electrons are being moved from point A to point B quite readily. Okay. All right. Which brings us to covalent bonds. Now, we have 3 types of covalent bonds. And what can be done sometimes is they can be written out, and I'm going to do that. Okay, I could have, for example, what we call a single bond, and that's simply 2 electrons being shared between 2 atoms. So I'm going to write that by, say, carbon, hyphen, and carbon, and that represents a single bond. That is the bond between these 2 is a single bond. Now, what that line represents are basically 2 electrons. And so I can write that with the 2 dots, right? So if you have a lot of bonds, that's a lot of dots to be written. So what happens, you'll see it quite often, is a line is written to represent a bond or 2 electrons, okay? Now, we also have an example of a double bond, which could be written, I can use the equal symbol to designate two lines or 2 of these that represent a double bond, okay? And each line is 2 electrons. So in a double bond, there are 4 electrons that are being shared between these 2 carbons, okay? 4 electrons, that's a double bond. Then it's going to be a little more difficult, but I'll give it a shot. I'm going to do it this way. I got to come back and draw something. Well, okay, this is eventually going to be a triple bond. Okay. But I could come back and draw another line here. Give me a second. All right, let me see. Draw a triple line and all right, it's red, but actually I thought I had it in blue. Okay, so that red line represents another bond. So it's a triple bond, okay? a triple bond. So we have single bonds, double bonds, and a triple bond. In a single bond, we have one electron. So every line represents a 2 electrons that are being shared. You may also see them in these what we call space-filled models like this, where this represents carbon dioxide. We have the carbon in the center and then the oxygen atoms to the left and to the right. Now, the formula written out is obviously there, carbon, and then the subscript 2 to represent 2 oxygen atoms. This is an example of a space-filled model for the formula H2O. I said earlier that in general, 99% of the time, the first atom in covalent compounds is the central atom. So we have the central atom, and then whatever follows is bonded around it. And normally that happens. But occasionally, for example, water by convection is written as H2O. The hydrogens are not the central atom. The oxygen is. So it turns out it's the next one. And so that's only the exception, H2O. But you always will know who is the central atom because it will be written, it will be either in bold, okay, or there'll be an underline underneath it to tell you this is the central atom, and whatever follows is bonded around it, okay? So we got single, double, and triple bonds with respect to covalent compounds. Okay, and that's basically what I just stated. Now, single bonds are, there is a length between them, between the two atoms. We have a bond length that we can measure indirectly, but it can be measured, okay? They tend to be they are the longest and the weakest with respect to energy. Now, triple bonds are extremely short, so it kind of pulls these two atoms together. The ones that are sharing the triple bond are much closer, and they tend to be the strongest and have the highest amount of energy. In fact, single bonds, a good example of that would be like butane, like your lighter, propane, or you're out there cooking your hamburger. They give off heat, but not enough to burn steel. For example, acetylene. Acetylene is a triple bond species, and there's a lot of energy when you mix that up with oxygen, strong enough to use it to cut metal. So a lot of bond energy there in the triple bond. Okay, now it was thought that with respect to covalent bonds, that when they came together, that the sum of each one's radius would be the bond length between the two electrons that are being shared. And so if we look at the radius of, let's say, the hydrogen atom, okay, we find it to be 0.37 nm, which is nanometers, very tiny. That's the atomic scale. The hydrogen atom has that diameter, okay? The chlorine atom has a diameter of 0.99 nanometers, okay? So it was thought that when they came together to form a bond, to form HCl, that their bond angle would be the sum of each individual bond angle. So the sum would be about 0.136 nanometers. But that's not what was determined. It was found that the bond angle between the hydrogen and the chloride molecule is actually much less than what was predicted, 0.127 versus 0.136. And so what is happening is when it forms a covalent bond, there is an area of overlap between the two. And hence the bond angle is much less than the sum of the individual radius of the two atoms. There's a bond angle where these electrons are just pulling each other a little bit closer, okay? Now, also, there is a dipole. Think about this. There's dipole. Remember we were talking about electronegativity? Okay. There's a dipole, meaning there's going to be two poles. Now, if we look at the electronegativity of chloride and compare it with the hydrogen, who is more electronegative, hydrogen or chloride? Using the periodic table, who is more electronegative? When we're looking at the bond right here, who is more electronegative, the chloride or hydrogen atom? Find their position on the periodic table and which one is closer to fluorine. Okay. The chloride, exactly. Okay, hydrogen is way on the other side of the periodic table, is in group one. The chloride is right underneath fluorine. Okay, so from a electronegativity perspective, chloride is a lot more negative. It has a higher EN, electronegative. So what that means is, and I'm going to draw a little arrow that goes from the hydrogen. Oh, no. I'm going to draw a little arrow that goes from the hydrogen to the chloride. What that is saying is this, that because the chloride is a lot more electronegative, that in that bond that I wrote there, that I drew that red arrow in that diagram, the chloride is pulling the electron density toward itself much more than the hydrogen is. The result is that on the hydrogen side, there is a little partial positive charge to it, much like the balloon, if you will. But this is a permanent thing because of the electronegativity of the chloride. It causes electron density to get away from the hydrogen, giving it a positive character, positive nature to it. Okay, and the chloride now, because of higher electronegativity, now has a more negative nature to it. So it has a partial, not a full-fledged charge, but what we call a partial charge. And that creates a dipole, just like we do with the balloon where we created a temporary dipole. The thing is that this formula, this structure has a permanent dipole. And if you can imagine, think about this for a moment, I got this little, think of the HCl as a little magnet with the north and the south pole. And if I had other little magnets, wouldn't they all line up? The north would attract the south and one magnet and so on and so forth, right? Everybody would line up. And that effect affects the overall property of hydrochloric as far as the boiling point, things like vapor pressure, some other properties, all related to the electronegativity of the atom and how it affects the electrons around it. Okay. All right. So anyway, just an introduction to that. We'll come back to that. So the bottom line of all this is that the bond length is much smaller than the sum of the individual bond radius of each of the atoms, and that is because there's overlap. There's overlap in that bond, okay? And that covalent bond, I should say. So bond energy. When we talk about bond energy, that is the amount of energy. It's all boiled down to energy. Chemistry boils down to electrons because that's what's happening in chemical reactions. All the action happens with electrons. You know, you're going to have them or don't have them or you're going to move them around to get something to happen. Also, it's related to energy. You got to have sufficient energy to either to break a bond or to form a bond. Okay, with respect to even even ionic compounds, it takes energy to break up that electrostatic attraction. Even more so with respect to covalent bonds, because these bonds are being shared, and it takes a lot more energy to break that shared bond. Okay. So all about energy. Now, thing is about breaking a bond always requires energy. Okay. I got to break something to create something else. It requires energy. So uh, energy is what we call a reactant, and it is absorbed, which means it gets cold. It's an endothermic reaction. Endothermic meaning, and I think you've seen or maybe used some of these. If you go to the pharmacy and you buy yourself a cold pack or a hot pack, and you take that pack and you smack it, depending which one you bought. If you bought a cold pack, guess what happens to that cold pack? It gets cold when you smack the ingredients inside the container. We call that an endothermic reaction because whatever that reaction is occurring is taking energy away from the environment, the system that is the outside system, and it's making it cold because it's withdrawing energy for that chemical process to occur. It's absorbing energy. Okay. And so when we write a reaction, heat or energy is part of the reactants. What do we mean by the reactants? To refresh your memory, when we write a chemical process, we have an arrow here. To the left of the arrow are the reactants. To the right of the arrow are the products. So in this case, we are breaking up hydrogen chloride because it's a gas here. Okay. We're breaking it up to their respective atoms, okay? And that requires energy. And it takes the energy from the environment, which results in having a cold reaction. It is called endothermic. So breaking bonds requires energy, okay? And that results in an endothermic process. It gets cold. Forming bonds releases energy, okay? And that is classified as an exothermic reaction. It gives off heat. Same pharmacy, you go buy a hot pack, okay? It's a hot pack. You have a package and you crush them, get the ingredients mixed up in there. It gets warm. So you can put it on your sore muscles, wherever, or who's ever hurt, okay? It's warm because it's giving off heat. It's an exothermic reaction. That means whatever chemicals are in that container, there's a lot of bond breaking going on, okay? Because it's releasing energy. And therefore, heat or energy is a product written here, okay? So breaking bonds requires energy. Heat or energy is a reactant. Forming bonds releases energy. Heat or energy is a product. Okay, remember the arrow designates a process, chemical process, either physical or chemical. Okay, and to the left of the arrow are reactants, and to the right of the arrow are products. So, true or false? Electrons, number this one here, H2S, very nasty smelling gas. Hydrogen sulfide is called. Electrons are shared in H2S. What do you think? Okay, well, that would be a true statement. That is correct. Okay, because remember, if we have hydrogen, we have sulfur, both nonmetals. Both nonmetals means we have covalent compounds, covalent bonds. Covalent bonds tells us these bonds are being shared with the atoms. There'll be equal sharing and not equal sharing, but in this case, We'll get to that, but right now they're just being shared. Okay, so that's a true statement. The bonds between hydrogen and sulfur is ionic, and that's not a true statement, right? Because we just determined hydrogen's non-metal, sulfur's a non-metal. Okay, so that's a false statement. The bond is a covalent bond. One of these was a metal, then it would be ionic. For example, we could have easily wrote Na subscript to S, okay? Sodium sulfide, okay? And so question number 1 would be false because that's ionic. Nothing's being shared there for sodium sulfide. But for hydrogen sulfide, that's a true statement, okay? Question number 2 for sodium sulfide would be true. But for hydrogen sulfide, it's false. Okay. And so let me move this guy over here. So the answers here would be for this would be opposite of what you see here for sodium sulfide. So the bond length, the HS bond length is less than the sum of the 2 atomic radii. Okay. And that's a true statement here. Yeah, that's correct. Now, that wouldn't be that would be not even a, you couldn't, for sodium sulfide, there's no bond length, okay? They have their own respective radii. So that question number 3 wouldn't apply for sodium sulfide because remember, there's an electrostatic attraction for sodium sulfide. And then breaking the HS bond releases energy, okay? That's a false statement, okay? Because breaking the bond requires energy. Remember that. All right. Which brings us to Lewis dot structures. All right. Well, the first thing is we're going to be Lewis dot structures, very straightforward. They basically represent the valence electrons for a particular atom. Okay. And we draw them by just putting a dot to represent the valence electrons in the outermost shell. We're going to need to learn, this is just for the atoms, and then eventually we're going to talk about Lewis dot structures for compounds. This is the beginning. So based on the group number, and this is only true for the A elements, group 1A through 8A, okay? We simply put dots around the atom for the number of valence electrons the atom has. Okay, and what we do is we go around the circle. So if we start with 1 dot, whatever you want to put it, there's going to be two, think of it as a square. So the top square, you're going to put 1 and go around to the side squared and to the bottom squared and to the far left. And then if you got more than 4, then you fill up the 5th one. So you're going to have two dots. So let me draw it this way. Think of it as a square. Okay. And so we're going to put a dot. Okay, you can start it anywhere. You can start, say, right here. That represents a dot. And then here's another dot for 2 valence electrons. And then we go around the horn, so to speak. Bottom of the square, that's supposed to be a dot. And then we go to the left of the square. And then if we got 5 valence electrons, then we go to the top. So there's 5. There's 5 electrons, and then there's 6, and then 7, and then finally 8. Okay, so now we got 8, and that represents group 8 valence electrons, and then the elements in the center, whatever the element we're dealing with. Okay, so you go around the square before you, because you fill up. You don't want to put 2. You only got 2 valence electrons. You don't want to put them in the same side. Separate them. And then until you're full with the 4, just go around. You're filling up the orbitals like we did with the electron configuration. So for the atoms, if we need to know the Lewis dot structures for, say, potassium, oxygen, silicon, magnesium, and iodine, all we do is find what group they're in, and there they are. Potassium is in group 1, so I got 1 dot. Oxygen's in group 6. Excuse me, 6. All right. And so I put 6 valence electrons. Silicon's in group 4. Magnesium in group 2. And iodine is in group 7. Okay. And if you had a noble gas like krypton, then you would have 8 dots, 2 in each side around it. So with respect to atoms, pretty straightforward. Find them on what group it is, put the number of dots in. All right. For structures, okay, what we do is we have to add up first the total number of valence electrons that every atom brings to the table, brings to the structure, okay? And then we put them together. We would tell you what the central atom is, okay? And once we do that, we can, for example, start putting what's bonded around the atoms sequentially, or put them all together, or either way you want to do it. We surround the central atom with the other atoms, and we draw a single bond between them, okay? And then we continue to add the remainder of the valence electrons that we have, remembering to maintain the octet, okay? And remembering the other aspect for hydrogen. Hydrogen will always have 100% of the time only 1 bond. So if you have hydrogens in there, that's all you're going to see, 1 bond. Okay? And then we check to verify that there's 8 octets around the atoms except for hydrogen, which I have 2. Okay. And then we on a check, we make sure that the total number of valence electrons that we put on the structure add up to what we calculated, okay? And then identify the bond, those electrons that are bonded and being shared, and identify the lone pair on the central atom. Why do I want to do that? Because once we do that, we can go through the shapes table after we created a general formula, and that general formula will tell us the geometry and the bond angle of the compound. Now, if for some reason we cannot put the octet around all the atoms, okay, then we start creating either double bonds or triple bonds. Now, this is important, okay? Let's say, for example, you add up a total of 8 valence electrons and you put them around your molecule. Well, you got 8 valence electrons. You cannot just throw in 2 just because you need to, nor can you take out 2 just because you don't need them. Okay? All the valence electrons you calculate are going to be used. If you are short, then we start creating double bonds. We start creating triple bonds until such time that the octet is fulfilled. And if you still can't get the octet to work, then go back and double check your mathematics. Make sure that you added up the correct number of valence electrons, okay? Because it's all related to that, valence electron. Okay. So let's try H2O. Very, very straightforward, simple form of compound. So you're given the formula, okay? And in this case, oxygen is the central atom. It's not listed here yet, but I'm telling you, oxygen is the central atom. And hydrogen is bonded around. The 2 hydrogens are bonded to the oxygen. All right, first thing we do is add up the valence electrons. So hydrogen, there's 2 hydrogens, and every hydrogen brings in 1 valence electron. So it's 2 times 1. And then oxygen is in group 6. It brings in 6 valence electrons. So we have a total of 8 valence electrons to work with. Okay, 8 total electrons to work with. When you add up your valence electrons, you should always end up with a number divisible by 2. And so 8 divided by 2 equals to 4 pairs, okay, that you have to work with. I prefer to make them into pairs because now I can just draw a line. Remember that line represented a pair, and it's easier for me to keep track of the number. Just calling them pairs and drawing a line. So I got 8 valence electrons or 4 pairs of electrons to work with. Okay. All right. So we know that oxygen is a central atom, so we can very quickly draw, and I'm going to draw it this way. I'm going to get my drawing pen for next time so I can draw some stuff here, but right now I'm going to do it longhand. And so I have hydrogen bonded to oxygen that is bonded to hydrogen. Okay? See how I did that? If I was drawing now, I would draw oxygen and then 2 lines that represent the 2 hydrogens. Guess what that did? That is 2 pairs, okay, of electrons that I've taken care of. And so I have 4 pair that I started off with. 4 minus 2 equals 2 pair left to work with. I got to put them someplace. Now, remember hydrogen, its magic number is 2. So hydrogen has a pair bonded and shared with oxygen. So that line on each hydrogen, those pairs are being shared by both the oxygen and the hydrogen. Therefore, count each one. So the hydrogen has 2 electrons around it. Each one has 2 hydrogens around it. And right now, oxygen only has 4 total electrons or 2 pair around it. So I got 2 paired left. I got to put them someplace. I can't put them on the hydrogen because that will violate the Duet rule for hydrogen. So the only logical place that they belong is on the on the oxygen. So what I do, let me make sure I got everybody in blue here. I can very simply draw a line on the oxygen, okay, like so. And guess what? Now I still have 4 pairs. Now count all the lines around oxygen. I got 4 lines around oxygen. 2 of them are bonded with the hydrogen, and 2 are, remember, the lone pair? Those, I got 2 lone pair sitting there, okay? And do I still have 8 valence electrons that I begin with? Yes, I do, because each line that I wrote has 2 electrons. So I got 2, 4, 6, 8. So I've not violated the number of electrons that I have to work with, okay? So it's still 8 valence electrons or 4 pair. So that is the general formula that I come up with. Now I create the general formula, the ABE, okay? Now, I look at A, there's always one A, and that is the oxygen. That oxygen represents the A. There are 2 Bs, right? Because there's 2 hydrogens, so that's B subscript 2. And guess what? Because it's got 2 lone pair on the oxygen, there are 2 E's. Okay, so keep in mind, those are subscript. A, B2, E2. That is our general formula. Now, where do we use that? We go to the shapes table, okay? Go to the shapes table. So from the shapes table, we look for the general formula AB2E2. And guess where that is? Right here. So water, its particular geometry is that shape. There's the two lone pair and the two hydrogens. The name of that shape is called bent. And that bond angle between the two hydrogens is much less than 109.5. Much less because those two lone pair take up a lot of space, and that bond angle is crushed in. Okay. All right. So you see how we came up with that? Okay. So that information, that is a general formula that we come up with. I did it longhand, but it looked like something like that. And I know that based on the general formula, AB2E2, remember the E represents the lone pair on the central atom only. And there's two lone pairs. So it's AB subscript 2, E subscript 2. Okay. And that gives us the name of this particular shape, bent and that bond angle. All right. Now, let's try these. Okay. Now, we have, let me see something here. Oh. We have, this is going to be a fun one, okay? We have HCN, hydrogen cyanide, poisonous gas. Okay? You are given the central atom, which is carbon, okay? And then that means that hydrogen and nitrogen are bonded to the central carbon, okay? So what we got to do is first count up the valence electrons. So hydrogen, I'm going to draw over here to the right. Hydrogen brings in 1, right? Hydrogen valence electrons equal 1. Carbon valence electrons equal 4. Okay, we got 14 so far for HCl. Okay, let's see. And then nitrogen, what group is nitrogen in? It's in group 5, is it not? Okay, double check my number. Hydrogen's in group 1, has 1 valence electron. We're doing the first HCN. Carbon is in group 4, has 4 valence electrons. Okay, and 5 for nitrogen. Yeah, no problem, Kathleen. So we got a total equals 10 valence electrons, or guess what? 5 pair. Okay, because 10 divided by 2 gives me 5, right? I got 5 pair to work with. All right. Now, since carbon is the central atom, I can very quickly, I can draw hydrogen, carbon, and nitrogen. I can do that drawing. If I was doing it on paper, that's what I would do first. Carbon with the central atom and just attach the other 2 species there. Okay. Well, that took care of 2 pair, did it not? Right. So now I have how many left? So 5 minus 2. I got 3 pair to work with left. Remember, I cannot go more than 5 pair. This is what I got to work with. All right. So now I can do the 5 pair that I got. I can put them anywhere I want. Now I can't put them on the hydrogen, right? Because the hydrogen's already taken care of. The hydrogen has 2 electrons around it, being shared with the carbon. The carbon right now is sharing only 1 pair. So those 3 pair, I can put them anywhere between the carbon and the nitrogen. So I'm going to just put them, I'm just going to put them, let me draw them. I'm going to draw a line, and I got 3 pairs, so I'm just going to very arbitrarily just put them right here. I put one there, and one there. Y'all see that? Okay, now count my lines. Do I still have 5 lines or 5 pairs? I got 1 between the carbon and hydrogen, and 1 between the carbon and the nitrogen, and I got 4 around nitrogen. You all see that? That's a total of 5 pair with 10 valence electrons. So I got to keep track of that because I can't remember. I cannot add more or take more. This is what I got to work with. All right, so hydrogen's duet is happy. We're done with hydrogen. Nitrogen has 8 electrons around it. Nitrogen's happy right now, okay? But carbon only has 2 lines or 4 pair. So it doesn't have the octet. Nitrogen does the way it's written, but not carbon. So what do? Carbon is missing 2 pairs. So we create a double bond, a triple bond. We take 2 of those on the nitrogen and share them between the carbon and the nitrogen, okay? And guess what we make? We make a formula that looks like this, right? Do we still have 5 pair around everybody? Yes. We got 4 lines, 1 on the carbon hydrogen, 3 lines at between the carbon nitrogen, and then a lone pair on the nitrogen. Is the octet fulfilled for every atom or the duet? Well, hydrogen is sharing 2 electrons. Remember, when it shares, it counts both toward this pair right here. It's 2 electrons. We count it toward the hydrogen and toward the carbon because it's being shared. So there's 2. So hydrogen's happy. Carbon is sharing 6 electrons of nitrogen and 2 more with the hydrogen. So its octet, let me get rid of this. The number around carbon, number of electrons around carbon is 8. Its octet is full. And then finally, nitrogen, it has 8 around it, okay? 8 around it, 3 of them are shared with the carbon and 1 pair on the nitrogen, lone pair. Now, we write the general formula, but I'm thinking that you can see that it's linear. But if you didn't know that, what would be the general formula for this formula that we just structured, that we just put up? What do you think? We got A, right? Which is the carbon. Do we have B? Yes, there's 2 B. Do we have any E? Not on carbon. Remember, the lone pair is only for the central atom. So the general formula is AB2. You go to the shapes file, okay? AB2, the very first one, AB2. Its geometry shape is right there written. Its name is called linear, and that bond angle is 180 degrees. So on one side of the central atom is you got carbon in the middle, and you got nitrogen on one side and hydrogen on the other side. Okay. So that one is consistent. All right. The next one is a little more challenging because all you got to do is you got to add more. Okay. So but the same scenario. All right. So let's do this. All right. So we're gonna add up. We got 1 carbon. So we're gonna add up the valence electrons. So carbon again brings in 4. Okay. Hydrogen, again, brings in 1. And we got 3 fluorides. Okay, what group is the fluoride in? It's in groups. Oh, did I say 2? Sorry. 3 of them. Okay, each one brings in how many? Isn't that 7? There's in group 7, right? So 7 times 3, wouldn't that be 21? And so the total number would be 4 plus 1 is 5 plus 21 is 26 valence electrons, or how many pair? 13 pair, right? Thirteen pair. And that's what we got to work with. Now, the challenging part for me, we'll be trying to draw this. Let me see what I can do. All right, we got hydrogen. I'm going to put hydrogen in 1 bond, and then we got carbon, 1 bond, and then I'm going to go ahead and put a fluoride. Okay. All right, can I put a fluoride there? And can I put, yeah, I'm going to do it this way because I don't have the drawing capabilities. All right, so now I'm going to put a line. How much still in blue? Put a line right there and a line right there. Okay, so carbon is a central atom. Around it is bonded the 3 fluorides and the 1 hydrogen. Okay, and so I can very quickly put the carbon in the middle and then attach those 4 atoms around the central atom. Okay, and that takes care of 4 pair. Okay, I have 4 pair. Now that leaves me how many? How many more do I need to work with? I start off with 13. I just used 4 pair to draw the general formula right now, the general structure. So I can subtract 4 from the 13. What do I got left? I got 9, right? Okay, good. So I got 9 to work with. Now, I cannot put any more in hydrogen for the same reason we did before. It's a duet. There's 2 around hydrogen. I can't put any more around carbon, right? Because carbon, guess what? It's full. I got 4 lines around carbon. Okay, I got 9 pair to work with. That's correct. Okay. And so the only place I can put them is where? On the fluorides. So I got 9 pairs left, and I got to put them on the fluoride. So I'm going to very quickly draw a line here. Bear with me. That's supposed to be a line there, 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 there, there. One more. Almost got it. All right. Kind of not the best structure. Obviously, it was on the board, it'd be a lot better, but count the number of lines we got there. Do we still have 13 total? Yes, we do. 13 total. We got 1 shared between the hydrogen and the carbon. We got 4 around the carbon. Okay. Well, the other 3 around the fluorides and the one with the hydrogen. So that's 4. And then the other 9 have to go around the fluorides. Okay. So the octet is fulfilled with everybody. The fluoride has 8 electrons around it, each of the fluorides. The carbon has 8 around it, and the hydrogen has 2 around it. So guess what? Everybody's happy. Okay. We go through the general formula, and that becomes A, B, 4. Right? AB4. And that becomes tetrahedral. If you look at the shape table, it is tetrahedral. Okay. All right. I tell you what. Let us stop it here. 7, page 19. Because to draw the other ones, I really got to get my little drawing panel and see if I can get that thing to work so I can actually draw things. And it'd be a lot easier than trying to do it the way I've been doing it. Okay. So let us stop it here. We'll stop at slide 19, chapter 7. And